This is a quick review about Fourier transform. The outline of the lecture goes like this. We will start with the definition of Fourier transform. Then we will go into tables of some important Fourier transform pairs. Then we'll get to the table of properties. And then we'll use Fourier transform in transmission through linear system analysis. And finally, we'll go into ideal and practical. Now, let's relate Fourier transform to Fourier series. What you see here is a complex Fourier series. And here is the magnitude spectrum, which is the spectrum, a sketch of the magnitude of dn. Since this is discrete, you can see that we have spectral lines. Okay, d0, d1, d2. Now, what happens if our signal is not periodic, it's aperiodic? If that's the case, the period will tend to infinity. And the frequency, which is the inverse, the fundamental frequency, which is the inverse of the fundamental period, will tend to 0. You know that these spectral lines are spaced by multiples of the frequency. So if the frequency tends to 0, those spectral lines will get close to each other and we get a continuous spectrum. So the first thing to note, for periodic signals where we use Fourier series, the spectrum is made of spectral lines. So just by inspection, I can say this is periodic signal. And if the lines get close to each other, that makes them make a continuous line, then we have the spectrum of a non-periodic signal. So here are some notations. If we say script f, if g of t equals to capital G of f, this is the Fourier transform. You use capital letters as function of frequency to represent the Fourier transform. We use the inverse Fourier transform for the following notation. So the inverse Fourier transform of capital G of f give you the function in time. We use a double arrow to indicate that these are Fourier transform pairs. Sometimes we use omega or f, the angular frequency, or f measures in hertz. And of course you have to be careful when you use one or another. So a non-periodic signal is usually represented by Fourier transform. Now, if you compare the equation, this Fourier series, with the following transform, you can see that they are very much the same, except in continuous domain we use integration instead of summation, and then we are just using 2 by f to represent omega. So there is direct relation between Fourier transform and Fourier series. If you want, you can also find g of f, the Fourier transform. This is in terms of g of t. So this is the inverse Fourier transform equation, and we can also write capital G of f to be the following. Notice that here is a minus sign. This is the widely common equation, widely used equation, because this gives you Fourier transform, and later on we use the inverse Fourier transform. Remember, there's a minus sign in the exponent here, while there is none here. So, noting the fact that Fourier transform and Fourier series are related, you can tell that the spectrum will always be even magnitude, odd phase. This is how we write odd, and this is how we indicate even magnitude. Adding these two together give you what we call the complex conjugate property. So if capital G of f is a complex function, we can combine the two properties by saying G of f equal to G conjugate of minus of f. Okay, now also remember that Fourier transform is a linear operation. That's to say, if you have a function g of 1, g sub 1, which has a Fourier transform capital G1, another function g sub 2, which has a capital G of sub 2 as a Fourier transform. Now you can also make a linear combination by scaling and adding, and you can readily get the Fourier transform. Now, example, if somebody gives you the following equation and he wants to find the Fourier transform, then we can say that exponential e to minus a of t u of t. How do you find its Fourier transform? Direct application of the equation. So here we apply the equation. This is the Fourier transform equation. Now the impact of u of t is to change the integration limit from 0 to infinity. And now two exponents multiplied by each other, we can combine them together. And then you can just integrate the exponential. Remember that everything here is constant, so we divide, we integrate, substitute the limit, and we get 1 over a plus j infinity. Remember that a has to be positive, otherwise e to the power minus infinity will not tend to 0. So this is the condition that must be met. You can take this complex representation, you can find its magnitude. Now remember, the magnitude of a complex number is square root of real square plus imaginary square. And we also write the angle in the exponent, so e to the minus j. The fact that there is j means what we have here is just an angle. It's tan inverse omega over a, and because it's in the denominator, we have a minus sign. Okay, so the magnitude is this and the phase is that. We can write in complex form, polar form, or separate form. If you want to sketch the signal itself, here is how it looks. It's dying exponential, and because it's multiplied by u of t, it starts at 0. Now the spectrum itself is a complex function. This is why we have two sketches, one for the phase and one for the magnitude. This is two different functions. Okay, now let's find the Fourier transform of some important functions. The first function is the delta function, or the unit impulse function. If you apply the equation, the Fourier transform of delta, this is the integral Fourier transform equation, you can apply the shifting property, and that would give you 1. So the Fourier transform of delta in time is 1. The second function we are interested in is the rectangle function. The rectangle function mathematically is defined like this, and maybe it's easier to show it on the diagram here. So it's 1 in the middle and it's 0 outside. Just to avoid the ambiguity in this corner, we're going to define it to be half. So for the case of width equal to 1, it goes from minus half to plus half. So it's 1 here and 0 outside. At the corner, we can say it's half. And this is why in the piecewise linear definition, it's 1, 0, or half at the edges. So again, if you want the Fourier transform of the rectangle function, you apply the equation. The impact of this multiplication by the capital pi function, or the rectangular function, is to limit the integration from minus tau over 2 to plus tau over 2. Now, if you execute the integration, this is just a dummy variable, because our variable is tau. So when you integrate an exponential, you divide by that exponent, and now substitute the limits. Looking at this expression, an exponential to j theta minus e to the minus j theta. This reminds you of what? This reminds you using Euler identity with the sine function, especially that we have 2j here. So all of this together will make a sine function. Okay, this blue part of the expression will be transformed into sine. Remember that sine theta over theta is also sinc. To get the sinc function, we need to multiply up and down by tau. Since we have the following expression, I'm going to divide by tau. I already have pi and f. I need tau, so it becomes perfect. So we get pi f tau in the denominator, and then we get what we have as sinc. This is sinc, and what remains outside is tau. So the rectangular function is making what is the sinc function? Quickly, if you don't recall, a sinc function is also called the interpolation function, and it's sine x over x, and it's, if you like, if you draw the envelope of 1 over x and its mirror images, this is 1 over x minus 1 over x, then you fill inside with the oscillation. If you want to evaluate sinc at 0, you'll have a problem, because sine 0 over 0 will give you 0 over 0, and then you need to use L'Hopital's rule, and that will give you 1. So it's 1 here, it oscillates, it crosses 0 at multiples of pi, because sine pi, sine 2 pi, 3 pi is all zeros. Okay, just a warning that some books define sinc to be sine by x over by x and not sine x over x. Now, in addition to the sinc and the rect function, we have we need to define the unit triangular function. It's like a triangle. It goes from minus tau over 2 to plus tau over 2. And we are going to refer to that using the triangular notation or delta notation. The width is controlled by tau. Let's recall the meaning of bandwidth. Remember, for the case of rect, we got the spectrum to be sinc. And if you are interested in the amplitude only, you'll get the sinc squared. This is sinc, but we square it because we are interested in the amplitude of the spectrum or the frequency representation. So what is the bandwidth here? How much bandwidth mean the range of frequencies that we have? Ideally, it goes from minus infinity to plus infinity. But to have a practical meaning for bandwidth, we define it to be the difference between the highest significant frequency and the lowest significant frequency. So if you look at this, we have high power here, the power decays. So we might think about the main lobe or the main beam as the bandwidth. This is one way of looking at the bandwidth. Still, we have something here, but the value is relatively small. Now, you will notice here that the bandwidth is inversely proportional to the time duration of the pulse, because pi t over tau give you sinc tau. So we have inverse relation. So if you want to have your sharper pulses take shorter time, send more data, it will be inversely proportional to the bandwidth, which means you need more bandwidth. Now, other signals, if you apply the Fourier transform equation for cosine, for a constant 1 give you delta of f. Remember, we started with delta, we got 1 in frequency. Now we're doing the opposite. We have 1 in time, give you delta in frequency. A cosine 2 by f naught t will be transformed into 2 frequencies, 2 deltas with a scale of half. Now if you use pi, it's going to be a little different. If you use omega, then this is going to be scaled. All deltas will be scaled by 2 pi. Once again, this is a spectrum of a cosine, which would be the same, but because f and omega are related by 2 pi, the impulses will be scaled by 2 pi. So half becomes pi. Why? Because we want to maintain the area of delta to be equal to 1. Other important functions, including the signum function or the sine function, you need to review this if you don't recall it. It has a Fourier transform of 1 over j by f. Now this is a game note, because some of you have studied with textbooks that are using omega. Especially when you have delta, you have to be careful, because the Fourier transform of cosine in frequency has scaling of 1 over half, but in omega it's going to have a scale of pi. If we continue in the same way, we're going to build a table of Fourier transforms. Here is the serial number, here is the function in time, and the function in frequency. This is just a condition. It continues here. Now there are lots of them. I would suggest that you remember number 1, it's exponential, multiplied by u of t. 6 to 10, they are widely used, they are frequently encountered. 17 and 18, because these are mostly related to communication. Other ones, you should be able to use them once the table is given. Okay, because in real life we'll not get these functions directly, and to make the table more useful, we are going to augment this table with another table, which is a table of properties, Fourier transform properties. Okay, since we are just reviewing, you need to go over these properties: superposition or linearity, scalar multiplication. These two together makes the linearity. Duality, time scaling, time shifting, frequency shifting, time convolution, frequency convolution, time differentiation, and time integration. So please get yourself familiarized with the following table. Now, to go over some of these properties, we have the first property, which is duality. Remember that going from time to frequency is very similar to going from frequency to time, except for the minus sign here and bit of differences. So no wonder that going Fourier transform of g of t is g of f. Now if you take this function and replace the variable with time, you will get the opposite operation. So we'll have g of minus f, small g of minus f. This is called duality, and it makes sense because the relation is dual. Now, once more, another note: if we are using omega, the inverse Fourier transform will have a scale of 1 over 2 pi, because the df is related to d omega by 2 pi. Now, if you want to avoid confusion, just stick to your book notation, and then you will learn the difference as we go on. So in our case, we'll just stick with f. To illustrate the duality property here, a rect give you a sinc, then a sinc will give you a rect function. Remember that because of the fact that rect is symmetric around the y-axis, this minus sign is not clear here, because flipping around the y-axis of an even function give you the same answer. Another important property is the scaling property. The scaling property is given by this: if you have a Fourier transform pair and you scale your time factor, if you multiply by a, the opposite scaling will be done in the frequency domain. So if you multiply by 2, you have to divide the frequency by 2. Also, the magnitude itself will be scaled. So two things: we have a change on the variable and change on the y-axis, on the magnitude. If you want to prove this, you can use the Fourier transform definition, and we can do a change of variable. If you replace this variable with x, execute the change of variable, you will have dt now becomes dx over a. You can see the red colored here dt will be replaced by dx over a, and then the new variable x replaces a of t. And you can see all what changes is, if you compare this with the Fourier transform of g of t, you'll find the only difference is that we have scaled f by a, and we have another scaling outside. We did this for the positive, we can repeat it for the negative, and then we can combine the two definitions with an absolute value. So whether a is positive or negative, this is always valid. The importance of this, or the significance of the scaling property, is that if you have a pulse and you want to scale it down, if you want to shrink it in time, like you want to send more data, then you have to pay the price in bandwidth. The bandwidth will be greater. Shrinking time results in increasing the bandwidth. So it is inverse relation. Okay, here is an example. It says in this example, show that if you multiply the time by minus, then the Fourier transform will also be multiplied by minus sign. Recall that we have the following scaling property. What if a equal to minus 1? If you substitute a equal to minus 1, you will readily get this relation. So by letting a equal to minus 1 in the time scaling property, the above pair becomes, this pair becomes the new pair. Now we would like to use this fact and the fact that we have one Fourier transform pair to find the Fourier transform, the new function. If you compare these with that, the only difference here is we have a minus sign scaling. So you can tell that a minus sign scaling in time, if the time is scaled by minus 1, these are very similar, except the time is scaled by minus 1. So you expect the same Fourier transform, but the frequency will be scaled by minus 1. So we got the following relation. Now the next question is a bit tricky. It says find the Fourier transform of e to the power minus a of absolute value of t. That's a new one. But we have some information. Can we relate this to the two previous functions? If you look at the diagram, the sketch of e to the power minus a absolute value of t, it has the following shape. So we can relate it to the two original functions, and we can write it in this form. So we can say e to the power minus at equals to the decaying function, this part, multiplied by u of t to limit it to the right hand side. And we have the exponential increasing function, and we multiply by u of minus t to limit it to the left hand side. Now we already have the Fourier transform of these two functions. We can add them up. So adding them up, now we can still do mistakes here because these are complex conjugate. If you unify the denominator, you should get a squared plus 2 by f squared. That's a real function because they are complex conjugate. So you can do the operation and you should get the following answer. Other properties include the time shifting property, the delay factor. Delaying in time results in multiplying by exponential or phase change. So we can prove this by applying Fourier transform equation, and then we do change of variable. If we change the variable, a new variable, you will find out that you get back to Fourier transform but with a different exponent. So basically we can say that if we take this constant outside, okay, get this exponent multiplied by the Fourier transform. So we can say that we get the same Fourier transform scaled by a linear phase shift. Alright, so this shows that the delaying a signal by a constant time, seconds, does not change the amplitude spectrum. The phase spectrum is changed by a linear phase. Another important property is the frequency shifting property. It's the dual of the time shifting property. If you notice here, multiplying or shifting in frequency domain is equivalent to multiplying by complex exponential in the time domain. Now that says if you want to change the frequency content of your signal, all you need to do is multiply it by a complex exponential. But now, how in the lab we are going to multiply by complex exponential? Remember that a cosine is nothing but two exponentials. So we can define the modulation property, which is an extension of the frequency shifting. Frequency shifting is scaling by exponential. Modulation property, when you multiply by cosine, as if we're multiplying by two exponentials, one with positive sign, one with negative, and there is scaling of half. So no wonder a signal, when multiplied by cosine, it will result in shifting its frequency. And this is called the modulation property. So for example, we have a square wave here. Its Fourier transform, its frequency representation is the sinc function. When this square is multiplied by a sine function or a cosine, so when g of t is multiplied by cosine, you get this shape. Everything outside is 0, and then you get oscillation within the function. So what is the spectrum of the signal? If you know the spectrum of this, then you can notice here that I will get the same spectrum but shifted to the right and to the left, scaled by half, and this shifting is to the frequency defined by the cosine. We can use this property to perform frequency division multiplexing. We can take different signals and multiply them by different cosines with different frequencies and shift them, arrange them in the spectrum. This is very important. It's called the modulation property. We also can define the convolution property. G1 having a Fourier transform of G1, capital G1. G2 have a Fourier transform of capital G2. If you want to know the convolution, then you have to, if you want to perform convolution in time, it's a bit difficult. There is integration. Remember the equation for the convolution? Okay. But in frequency, you just need to multiply the Fourier transform. And if you want your signal back, you can go back to your signal. So please review your convolution, graphical convolution. If we have two basic signals, how do we get their convolution? Remember that the area and the resulting convolution equal to the product of the two areas, and the starting point equal to the sum of the two starting point, the end point equal to the sum of the two end points. For example, 2 is 0.5 plus 1.5. To get the exact shape, you have to perform the convolution. Notice that here that if you convolve a signal with width 1 with another one with width 1, you get the convolution to have a width of 2, the sum of the two widths. So multiplying in time results in frequency in doubling the spectrum. So sinc square will have double the spectrum of sinc, and sinc cube will have 3 times the spectrum. Bandwidth of product of two signals equal to the sum of the bandwidth. This is fantastic conclusion. Okay, we can also do time domain integration and differentiation. In the frequency domain, differentiation mounts to multiplying by j omega or j2 by f. Integration is dividing 1 over j omega. If you have initial values, you have to be a little bit careful. So we can also generalize the differentiation. If you differentiate raised to power n, that's the nth order differentiation. It's like multiplying j omega n times. There are examples in your book, and I advise you to visit these examples. Sometimes we are given a function, and we can find this Fourier transform by first differentiating it until we get squares or deltas. We can find the Fourier transform, and we can get back to our function by just scaling with j omega. Okay, so what's the advantage of all these transforms we have been through? One of the important advantages is I'd like you to know that the Fourier transform make analysis of signals and systems simple or relatively simple, especially if we have LTI systems, linear time invariant systems. Linear time invariant means does not change with time. So a system is usually defined by its impulse response or its transfer function. In time domain, we use h of t small, which is the impulse response, and in frequency, we use capital H of f, which we call the transfer function of the system. The problem with time domain, if you want to relate the output to the input, then we have to use convolution. So the output is the convolution between the input and the impulse response of the system. However, in the frequency domain, it's just the multiplication. The output is a multiplication. So if you want the magnitude spectrum, you just multiply the two magnitudes. If you want the phase, you need to add the two phases. So these two equations is the result of this complex equation. And if your signal is just sinusoid, you know that in any linear time system, the output will also be sinusoid, but with different amplitude and different phase. The frequency will remain the same. So in general, for nonlinear system, the output may be different than the input, but for linear systems, the frequency will remain the same. All what changes is the amplitude and phase. There is one type of systems which we call distortionless system. It's a very important type of systems. It's characterized by two things. The output is a scaled version of the input, and it's just a time delayed version of the input. So if you have x of t, and your output is just similar to x except for a delay and scale, we call this system distortionless. It does not change, it does not distort the input. Okay, so the condition for distortionless system is constant amplitude, fixed amplitude scale, and constant delay. If you apply Fourier transform equation here, you'll find that y of f equal to x of f times k times exponential. So also in the frequency, the magnitude must be fixed, but the phase is now not constant. The phase should be linear, which is function of frequency. We'll explain the meaning of linear phase as we go on in the next slide. This is a note. Again, distortionless transmission requires constant amplitude, constant delay, or in frequency, constant amplitude and linear phase and not constant phase. Recall that audio applications are sensitive to amplitude distortion. However, video applications are more sensitive to phase change. Okay, so why linear phase requirements? Let's see. Here are two different tones. Let's say that our signal is made of the sum of these two tones. If we want to keep our signal the same, we need to delay them by the same amount. So this is TD, the amount of delay that we introduce. Notice that if I move two signals by this amount, I have no problem. I can add them again, I get the same output. But if you want to talk in terms of phase, 360 degrees or 2 pi is equivalent to one full cycle. So from here to here. So this is 90 degrees. But for this different frequency, from here to here, we have 180 degrees. And from here to here, we have 360 degrees. So the units for the degrees depends on the frequency. This is why we need to scale the phase by the frequency. The amount of phase shift required from here to here is doubled because the frequency has doubled. Otherwise, if you don't do the proper scaling, you'll get phase distortion and your output will not be proper. Now let's conclude with the filters and one example. Ideal filters versus ideal versus practical filters. Now the ideal filters, we have different types of filters. A low pass filter allows low frequencies to pass and high frequencies to be suppressed. Of course, within the filter bandwidth, we'd like to make sure that the phase is linear. So this is the equation for the phase. The slope depends on the amount of delay. Okay, so mathematically we can say that the equation for low pass filter, it's a pi f over 2b, because the width is 2b here, and it's scaled by this complex exponent to represent the phase. What if there's no delay? Ideal filter, TD become equal to 0, and then we have only the magnitude response. But in real life we always have delay. Okay, now another filter, if you want to find the impulse response of this in time, you do inverse Fourier transform, you get sinc function. That's a good practice to go from here to here using the tables. So if you want to sketch this, you'll find that this is how it looks. The impulse response of the system look like sinc. And this is non-causal because it starts before 0. The impulse response should not start before the impulse. It should not start before 0. So that's, in real life, we cannot make an ideal low-pass filter. What we do usually, we approximate that by shifting and approximating things before 0 to be equal to 0. Other types of filters, including the band-pass filter, again, we need to make sure that the phase, at least within the bandwidth, is 0. It's not important outside because the magnitude itself is 0, so there is no meaning for the phase. This is called band-pass filter. We also have the high-pass filter. We can also have band reject or band stop filters. All right. Now, here is one example. I'd like to refer to the book here. I'm not going to spend the time here, but here we are showing a filter which is made of real circuit elements, R and C. You can practice by replacing that with inductance or change the order. So how do you find the transfer function of this circuit? Capacitance impedance is 1 over j omega c. If you use voltage divider, then the output is related to the input as 1 over j omega c divided by R plus 1 over j omega c, with a little bit of arrangement. And using the values given in the question, we can say that 1 over RC is given to be 10 raised to the power 6. So we can get the following sketch. You can see here that it's a distorting system because the phase, the amplitude is not constant, and the phase is not linear. It has some curve here. But we can approximate things. So this question is giving you some tolerance, 2% or 5% acceptance in terms of tolerance, and you can find the bandwidth accordingly. So you can find the maximum magnitude, and 2% of that is allowed, or 5%, and you say this is my bandwidth. Outside you'll have distortion. So you can freeze this to look at or visit this example and try to understand it. Thank you for being good listeners.